All right, and welcome everyone. In this lecture, we're going to talk about projectile motion problems that involved multiple objects. Okay, so we're going to do two different questions today. The first one says, a bird is flying east at a speed of 7.20 meters per second at an elevation of 23 meters. The bird then poops and it lands on a truck which is moving east along a level road with a constant speed. At the instant the poop is released, the truck is a horizontal distance of 1.25 meters in front of the bird. Find the speed of the truck and the time of flight of the poop. Gross. Assume that the truck is 3 meters high. Okay, so this question is similar to other projectile motion questions. We're going to start by drawing a graph of what's happening. So I'm going to just draw this graph. I'm going to label the x and the y axes. But this time we have two different objects, and there's a simpler object every time that's just moving in a sort of horizontal direction, and there's a more complicated object, which will be a projectile. Okay, so we'll start with a simpler object, and in this case, that would be the truck. Okay, so at the instant the poop is released, the truck is 1.25 meters in front of the bird. So let's say this is where the bird is, and the truck is 1.25 meters in front. Okay, so this is in meters. And then it says, find the speed of the truck and the time of flight of the poop. Assume that the truck is 3 meters high. Okay, so the poop has to land on the top of the truck. And so the top of the truck is, let's say, somewhere around here. And we're going to say that that is our 3 meters. Okay, I'll put my units up here. So here's my truck, and the truck is moving east, and we're trying to find the speed of the truck. So we're going to call this just VT for truck. Okay, that's what we're trying to figure out. So now let's move on to the bird, and actually it's the bird's poop that we're interested in. The poop is the projectile. Now at the moment that the poop leaves the bird is traveling east 7.2 meters per second, so that means the poop is traveling that direction as well. So that's the initial velocity of the poop, which is 7.2 meters per second. Okay, but it comes out of the bird, and so now it's acting as a projectile. So what is it doing? It's going to stop, it's going to drop, and it's going to land on top of this truck. Okay, so we want to make it land on top of the truck. It says, at the instant the poop is released, the truck is a horizontal distance of 1.25 meters in front of the bird. Find the speed of the truck and the time of flight of the poop. Okay, it tells you that the bird poops and it lands on the truck. Okay, so we're going to start by investigating the truck's motion. So I'm going to start here with truck. I'll do it down here because we don't need so much space. And what we want to do for the truck is we want to find the final X position of the truck and the final Y position of the truck. Okay, so for the final Y position of the truck, let's look at that first because it's simpler. We know that the height of the truck stays at 3 everywhere along its motion, right? So the initial point of the truck's position is 1.25 comma 3. But the final position of the truck's motion, we don't know what this value here. We can call it X final. That's for the truck. But the final Y position of the truck, we know it's still 3 because the truck is not moving vertically. Okay, so I'm going to just say Y final is equal to 3. And then in terms of the X final, we can use a kinematic equation. So I'm going to use this equation, S final equals S initial plus V initial delta T plus 1/2 A delta T squared. Okay, well, what do we know? The S final is what we're looking for. I'm just going to call that X final because it's specifically, we're talking about the X direction. The initial X position is right here, 1.25, plus the velocity of the truck. It's a constant velocity, it tells us. It tells us it's moving at a constant speed. So that velocity, we don't know what it is, but we called it VT. So that's what we're going to call it here. We don't know the time, so we'll say delta T. And because it's a constant speed, we know that this acceleration here is 0. So that means that the entire term goes to 0. So now we know the information about the truck's final position. We know the truck's final x position is 1.25 plus vt delta t, and the truck's final y position is 3. Now, because the bird's poop is going to land on the truck, that means that the final x and y position are the same for the bird. I mean, for the bird's poop. All right, so we're going to move on to the poop now, and I'm going to do that over here. But because the poop is a projectile, I like organizing all my information in a table so I can separate my x from my y. I'll put in the variables from the kinematic equation. And I'm not putting in v final here because the question doesn't ask us for the final velocity of the poop, and we don't know that value, so we're just going to leave it out. All right, so what do we know? The initial x position of the poop and the initial y position of the poop. So if I just label that point on this graph, so this is my initial position of the poop. If I label that, we would say that's 0, comma. What is that? So it says the bird is flying at an elevation of 23 meters. So this is 23 over here. So it'll be 0, comma 23. So that's what goes in our table. The final position of our poop, well, we wanted the poop to land on top of the truck, so we said that the final x position will be the same as the x position of the truck, which is 1.25 plus vt delta t. Vt is what we're trying to solve for, and delta t. And then the final y position of the truck, we said, is 3, so that would be the final y position of the poop because we want it to land on top of the truck. Okay, now we look at the v initial of the poop. So initially, it is flying, the bird is flying 7.2 meters per second. That's the speed the poop is going initially. So it is going in the x direction. It's positive 7.20, and there is no y component to that because it's completely horizontal. Okay, the acceleration in the x direction is 0, and in the y it's negative 9.81 because this is acceleration due to gravity, which points straight down. So there's no x component and the y component is negative. Okay, of course we're assuming that positive is to the right and positive is up. We make that assumption by drawing our x and y axes pointing to the right and up. So it's implied here. All right, so just like any projectile motion problem, we're going to pick the column that has the most information and then use that to solve for time. Okay, so which column has the most information? Well, the x column has some variables here that we don't know. The y column doesn't, so the y column is the one that has the most information. So I'm going to label that I'm working with the y direction, so I'm only looking at the numbers that are in the y column. So I'm looking for delta t. I don't know v final, and I don't need to know it, so I'm going to use the equation that doesn't include v final in it. And then I'm going to decide if I can cancel anything out. I know my v initial here is 0, so that means v initial becomes 0, and 0 times delta t, this whole term goes away. So I can just take that out. So I'll plug in everything I know. S final is 3. S initial is 23 plus 1/2. A is negative 9.81 delta t squared. Okay, so I can bring things to different sides so I can solve for everything. So let's bring this term here to the left side to make it positive since it's negative right now. And then we'll bring the 3 to the right side. So 1/2 times negative 9.81 is negative 4.905. And when I bring that to the right side, it becomes positive 4.905 delta t squared equals 23 minus 3, which is 20. Okay, now I can divide both sides by 4.905, and I get delta t squared equals, I'm going to type this on my calculator, 20 divided by 4.905. And I get 4.77472, and then I'll square root that, and I get delta t is equal to 2.0 19275. Okay, so when I'm answering the first part of the question, it says, find the time of flight of the poop. So that means how long is the poop in the air for until it lands on the truck. So my answer is this time here. So I'm going to say, therefore, time of flight of poop is 2.02 seconds. All right, so I'm rounding to 3 significant figures because all of my numbers have 3 significant figures in it. But on a test, you'll be told how many decimal places to put in. It will say always round to the nearest hundredth unless told otherwise. Okay, so that's my answer for that part of the question. It also wants the speed of the truck. So in my X component, in my X column, I can see I have this VT here. I'm looking for that. So let's move on to the X direction here. I'll write it here. Okay, so I have same idea. I'm going to use the same equation because I don't know V final and I don't want to know V final. And this time I take a look and see, okay, well, what's 0 here? S initial 0, so this term is gone, and A is 0. So A is 0, 1/2 times 0 times delta t squared is just all going to be 0. So that makes my equation a little bit easier. Now I'm going to start to sub in all the numbers that I know. So SF is this whole thing. So I'm putting this in for my SF, 1.25 plus VT delta t equals V initial, which is 7.20 delta t. But I just found delta t in my y direction, and the delta t is the same whether we're looking at x or y direction. Okay, so I'm going to put my delta t in. I'm not going to use 2.02 because that has a lot of rounding errors in it. I'm going to use a longer number with more decimal places. So I'm going to use the 2.019275. So I want to solve for VT, so let's do that right now. I'm going to rearrange the equation. So I'll bring that 1.25 to the other side by subtracting it, and then I'll divide both sides by delta t, and I get VT is equal to 7.2 delta t minus 1.25 over VT. Okay, so I'm solving, oh, that's wrong. Over delta t. I'm solving for VT. I want delta t to be gone, so I'm dividing both sides by delta t. So I put my delta t on the bottom here. So let's plug in our numbers. 7.2, my delta t is 2.019275 minus 1.25 over 2.019275. Okay, so I'm going to type this up on my calculator. And I get 6.58. That would be meters per second because it's a velocity. And this is my velocity of my truck. Okay, so I have more decimal places here that I can write down, but my question is asking what is the speed of the truck. So this is my final answer here, so I'm going to round it to 2 decimal places, which is also 3 significant figures. All right, so that's my final answer. I hope that question makes sense. We're going to move on to question 2, which is very similar. I just wanted to give you more practice. So if you feel okay with this question, try question 2 on your own. Here it is. And see if you can complete it on your own and set it up the same way. Okay, so we'll start off first by drawing our graph. So we have an x and a y-axis. And here, I'll read the question. A current causes a lily pad in the lake to drift at a constant speed of 1.37 meters per second. As the lily pad passes by a frog, the frog waits until it is a certain distance away and leaps towards it. The frog leaps at 3.7 meters per second at an angle of 24 degrees from the horizontal. How far away from the frog must the lily pad have been in order for the frog to land on it? Okay, so there's a lot of information happening here. So first it says what's happening is there's a lily pad and it's drifting at a constant speed. And then it passes by a frog. The frog waits for a little bit and then the frog leaps and lands on top of it. So at the moment that the frog is leaping, so let's say the frog is right here and it's leaping and it's at this angle that it tells us we're leaping at 3.7 meters per second. So I'll write that V initial is 3.7 meters per second at an angle of 24 degrees from the horizontal. So that's my frog leaping. And at that moment, there is a lily pad that is in front of it somewhere. So let's say the lily pad's right here. It's already passed by it. And the lily pad is traveling this way. And that frog is going to leap and it's going to land right on the lily pad. And so what the question is asking is how far away from the frog must the lily pad have been? So what is this x position here? The initial x position of the lily pad in order for the frog to land on it. So how long or how far from the frog is the lily pad before the frog jumps so that it will eventually land on top of the lily pad? Okay, unlike question 1, there's no mention about the height or the thickness of the lily pad. We're going to assume the lily pad is at the level of the water or the level of the frog. They're both at the same level. They're both on the surface of the water. Okay, so we're not going to worry about whether there's a certain height above the ground like the truck had. So we're going to solve this problem in a similar way. We're going to start with the object that is the least complicated. So in this case, that would be the lily pad. And we're going to decide, well, what is the final x position of the lily pad and what is the final y position of the lily pad? So I'll start with the y position. The final y position of the lily pad, we said the lily pad doesn't have a height. We didn't mention anything about that. We're just going to assume that it doesn't have a height. So the y position of it is just 0. It doesn't change at all. The lily pad is not changing its height. What about the final x position? Okay, well, we can use the same kinematic equation as before. S final equals S initial plus V initial delta t plus 1/2 a delta t squared. But we're talking about the x direction, so I'm just going to use x's instead of s's. Plus V initial delta t plus 1/2 a delta t squared. Well, we know the lily pad is moving at a constant speed of 1.37 meters per second. So I'll put that in my drawing. My velocity is 1.37 meters per second. Okay, so that's my initial velocity, but it's a constant velocity, so it's not changing. So my x initial, that's what I'm trying to find. That's what the question is asking. How far away from the frog must the lily pad have been in order for the frog to land on it? So we're looking for that x initial. My x final of the lily pad then, I'm going to plug in all the things I know is equal to x initial plus my v initial. This is of the lily pad, so it's 1.37 delta t. And since it's traveling at a constant speed, this acceleration is 0, which means all of this goes away. So that's my equation for the final x position of the lily pad. Like we said before, and I spelled lily pad wrong, so I'm going to fix that. Okay, like we said before, because we want our frog to land on top of our lily pad, its final x position also needs to be the same value here, and its final y position needs to be this, just like the poop that landed on the truck. Okay, so now we're going to move on to the frog. And because the frog is a projectile, we're going to have to make a table to organize all of our information. And we're going to put in all our kinematic variables, S initial, S final, V initial, A delta t. Question's not asking for V final, so I'm not putting that in. S initial, we're talking about the frog. So this is our initial position right here at the origin. So that's 0, 0. S final, we want the frog to land on the lily pad. So the S final of the frog is the S final of the lily pad. So the X component of that was the X I plus 1.37 delta t, and the y is 0. Okay, so we're using these numbers here. Okay, and the xi is what we're looking for in this question. That's what we're trying to solve for. Okay, v initial of the frog. So we're talking about this vector over here. It's 3.7 meters per second, but we need to find the x and the y components. So the x component is down here, and it's adjacent to the 24-degree angle, so we would be using cos. So it would be 3.7 cos of 24. It's pointing to the right, so it's positive. When we look at the y component, that would be this vector like that, and it's opposite of the 24 degrees. So we would be using sine. So it would be the hypotenuse, 3.7 sine of 24 degrees. Okay. So now we have the S initial, the S final, the V initial. We can move on to the acceleration. Okay, the acceleration of the frog. Well, the acceleration is that due to gravity. An acceleration due to gravity points straight down is 9.81 meters per second squared. So the x component of that is 0. And the y component of that is negative 9.81 meters per second squared. Right, so that's good for acceleration. And now time we don't know, that's what we're going to solve for. All right, so let's pick the column that has the most information, which would be the y column again, since the x column has some unknown variables in there. We'll start with the y direction. And we're going to use the same equation as before because we don't know v final, and we don't want to know v final. So S final equals S initial plus V initial delta t plus 1/2 A delta t squared. Excuse me. All right, so my S initial is 0. My S final is 0. And nothing else is 0. So let's start to sub in what we know. So we have 0 equals V initial, which is 3.7 sine 24 degrees. Delta t, we're looking for, plus 1/2 A is negative 9.81 delta t squared. So let's simplify all of this. We have 3.7 sine 24, and make sure your calculator's in degree mode. And we have 1.504926 delta t minus 1/2 times 9.81 is 4.905 delta t squared. Okay, so at this point, we have to solve for delta t. You have two options. You can use the quadratic formula. So this would be our A, and this would be our B, and our C would be 0. Or we can just factor out the delta t here. So that's what I'm going to do. It's a little bit easier. I'm going to factor out delta t, and I'm left with 1.504926 minus 4.905 delta t. Now I can solve for delta t. I get delta t is equal to 0, and delta t is equal to 1.504926 over 4.905. Okay, how did I get that? I can take each of my brackets, so imagine these are both brackets, and set them equal to 0. So my first bracket is delta t equals 0. That's done. My second bracket is 1.504926 minus 4.905 delta t equals 0. So I can solve for delta t. I'll bring the second term to the right side of the equal sign, and then I can divide both sides by 4.905. Okay, and that's what I got before, right here. So delta t equals 0, and delta t equals 1.504926 divided by 4.905, which equals 0.30681 4, 6. Okay, that's in seconds. Okay, so now we solve for delta t. So we have two possible values for delta t, but which value is it that we're going to keep? Okay, really what we're doing with this frog is we're figuring out how much time does it take for it to jump up and then land on the same surface again, so on the surface of the water in this case again. Well, when we set up our equation in our y direction, we're saying that final height is 0, the initial height is 0. So how long does it take for the final height to be 0? Well, initially the height was 0, so at 0 seconds, the height is 0, so that's one of our answers. But after 0.306846 seconds, the height is also 0 again. So it takes that much time, this much time over here, for the frog to jump and land at the same level as it started. Okay, so that is our delta t that we're using. So we can put that in our table if we like. 1, 4, 6. And because the x direction and the y direction for time, it would be the same since time is not a vector. It doesn't have x and y components. It's just the same value. It's a scalar. So we can put this in the table in the x direction as well. Okay, so now we have the time and we can move on to the x direction to solve for our missing value. So we're going to use the same equation. And what is it that equals 0? S initial is 0, so this is gone, and A is 0. So this is 0, so that means this whole term is going to be gone. So I have S final, which is xi, that's what we're looking for, plus 1.37 delta t equals V initial, which is 3.7 cos 24 degrees delta t. And I'm solving for this xi, so I can bring everything to the other side. 3.7 cos 24 degrees delta t minus 1.37 delta t, and I can sub in my delta t now. And my delta t is 0.306846 minus 1.37 times the same number. Notice I'm not rounding too much here because if I do, I'll get a big rounding error. My answer won't be accurate. So I'm keeping lots of extra digits. And so now I'm just typing this up on my calculator. Make sure your calculator is in degree mode when you do this. And I get 0.6167. I'm going to round 0.617 meters. Now, if we look at our question, how many digits do we have? We have 3 significant figures, 3 significant figures, 3 significant figures. So our answer has 3 significant figures. On a test, it will tell you how many decimal places to enter. And so the question might say, at the top of the test in the instructions, it will say round everything to 2 decimal places or to the nearest hundredth. And then it will say unless otherwise stated otherwise in the question. So if the question was like this, it might just leave it as 2 decimal places. So you'd write 0.62 meters, or it might specifically tell you leave your answer to 3 decimal places here. Okay, it just depends on the question. Canvas does not understand significant figures, so I have to specify on the tests, unfortunately. All right, so that's it. So we found out that the lily pad had to be 0.617 meters away from the frog the instant the frog decided to leap, and then that way the frog would land right on top of that lily pad. Okay, so these are questions that have to do with 2 objects where one is a projectile motion and the other one is just moving in a linear fashion. Okay, so expect to see a question like this on your test. Thanks so much for listening. Bye.